Let's practice solving a quadratic trigonometric equation that has a trig identity in it as well. Now, while these types of equations can often have an infinite number of solutions, we're just going to be focused on the ones between 0 and 360 degrees. And if we have to do any rounding, let's go to the nearest tenths place. To start, I'm just going to copy down this equation. So we have -2 multiplied by cosine of 2 theta. Now 2 theta means that we have a double angle going on here, so keep an eye on that. We have minus sine of theta, then we have plus 5, and on the right side we have 7 multiplied by sine of theta. Notice how we have a sine function here and here, but unfortunately we have a cosine function over here, and we also have a double angle. So let's see if we could swap one out using one of our trig identities. Now, while there's different forms of our double angle formula for cosine of 2 theta, I'm going to go ahead and use the one where cosine of 2 theta is equal to 1 minus 2 times sine squared of theta. So we only have one trig function in this equation, and that would be sine of theta. Subbing in that 1 minus 2 times sine squared of theta in for that cosine of 2 theta, we're going to go ahead and write that we have -2 multiplied by 1 minus 2 times sine squared of theta. Go ahead and make that substitution. Then we're going to have minus sine of theta plus 5. And on the right side, that's just going to equal that 7 times sine of theta that we haven't done anything with yet. Notice how we only have our sine function throughout this equation, so that's kind of nice. And while you can totally keep the sine of theta throughout the entire equation, I'm going to choose to go ahead and use some u substitution, and I'm going to do it now, but feel free to do it a little bit later if you want to. I'm just going to say let u equal the sine of theta, and just use u throughout the rest of this equation until we need to sub it back later. Swapping out u for each of these sine of thetas, we're going to have -2 multiplied by 1 minus 2 times u squared, and then we're going to have minus u plus 5, and this is going to be equal to 7 times u on the right side of the equation. Alright, so hopefully this looks a little bit less intimidating. I'm going to go ahead and distribute this -2 to both terms with the distributive property. That's going to be -2, and then plus 4 times this u squared, u to the second power, and then we're going to write minus u plus 5, and that's going to be equal to 7u on the right side. Alright, next I'm just going to go ahead and combine the like terms. We have -2 plus 5 on the left side, so that's going to be 4 of these u squareds, or 4 times u squared. Then we have minus u, and then that -2 plus 5 is going to be a positive 3, and on the right side we have 7u. So we have this quadratic equation that looks a little bit less intimidating than before, and let's go ahead and just turn it into standard form and move everything to one side to set it equal to 0. So I'm going to go ahead and subtract 7u from both sides. And when we do that, we're going to get this 4u to the second power. Take away what's -u, take away 7u, that's going to be minus 8u. And then we're going to have plus 3, and that's equal to 0. At this point, we have this trinomial. It's in this quadratic form, and we should try to see if we can factor it, but unfortunately we can't. So since it's not factorable, let's go ahead and try the quadratic formula. Okay, so in this case, we're going to go ahead and say that a is going to be 4, b is going to be -8, and c is going to equal positive 3. Now hopefully you know your quadratic formula, and I'm just going to go ahead and speed up this next process. If you need a little refresher on quadratic formula, feel free to check out one of my previous videos where I practice going through that. So plugging in that a, b, and c value into the quadratic formula, what we're going to find here is that x, or u rather, is going to be equal to 3 over 2 when we simplify this, or 1 over 2. Those would be the two ratios. Now keep in mind that this x over here was really just representing our u's back over when we were dealing with our equation that had that u instead. So we can go ahead and say now that u is going to be equal to positive 3 over 2. As well as u is going to be equal to 1 over 2. Now it's important to think back, what did we actually use this u to represent? So this u in each of these scenarios is representing sine of theta. So let's go ahead and make that substitution back. First, we're going to go ahead and say that sine of theta is equal to this ratio of 3 to 2. And then we also have that sine of theta is also equal to this ratio of 1 to 2. For solving this first equation on the left, if we're trying to find theta by itself, let's go ahead and say that theta would be equal to arc sine of this 3 to 2 ratio, okay? And then for our second equation over to the right, if we want to isolate theta, we can use that arc sine function again and say theta is equal to arc sine of that 1 to 2 ratio. Now, if you go ahead and plug this arc sine of 3 over 2 into the calculator, you're going to find out that this is going to be undefined. So keep in mind that this can only go up from positive 1 down to negative 1. So this positive 3 over 2 is outside of the possibilities for the arc sine function. Because this is undefined, we don't have to worry about any solutions coming out from there. However, when we plug in this arc sine of positive 1/2, we find out that theta is going to equal 30 degrees. Now hopefully this ratio of 1 to 2 for sine looks familiar, because we can find that in our 30, 60, 90 triangle. So hopefully that makes sense as a solution, and this happens to fit between 0 and 360 degrees, so we do like this solution. Now before we stop there, I do think we have another solution that we can find. So let's go ahead and use that unit circle to help us do that. So where's 30 degrees? 30 degrees is over in quadrant 1, maybe somewhere right about here. I'm just going to draw a reference triangle so it's a little bit more clear. 30 degrees is this theta right over here. Now we have a ratio of 1 to 2. Now for sine, that's y over r, or opposite over hypotenuse, however you want to think about that. So opposite of theta would be 1, or the y value. And then we have this 1 to 2 ratio, okay? Again, I know this is not quite perfect with the unit circle, but I think you get the idea with the ratios, hopefully. Okay, so yes, sine is positive over in quadrant 1, but we also know that hopefully that sine is going to be positive in quadrant 2 as well. So we can get that same positive 1 to 2 ratio if we go ahead and draw a 30-degree reference angle over in quadrant 2 as well. So right here, we can draw another triangle. This would also be theta, a 30-degree angle. Now, if we have a y value of 1 and a hypotenuse of 2, or opposite over hypotenuse, or y over r, we get that same positive ratio of 1/2. Okay. Now, while 30 degrees is just from here to here, okay, what angle measure do we get when we go all the way to this location in quadrant 2? That looks like it's going to be 30 degrees shy from 180 degrees. So if we take 180 and take away 30, we can also see that theta would be equal to 150 degrees, and we would still get that positive ratio of 1/2. Alrighty, so this would be our second solution for this equation, and our only other angle measure between 0 and 360 that would make this equation true. Summarizing this and putting it together, we can just say that theta would be equal to 30 degrees as well as 150 degrees. These would be the two angle measures between 0 and 360 that make our original equation true. So that right there just about wraps up this practice problem on solving a quadratic trig equation where we had to use an identity with double angles. If you found the video helpful, please consider giving it a thumbs up and sharing with a classmate or friend who might also find it helpful. And as always, keep up the great work that you're already doing, and I'll see you in the next one.